Hello everybody, welcome into another lesson. So today we are starting the unit on sequences and series. Sequences are going to be the topic of this lesson, and sequences you could simply think of as a list of terms. That's really all a sequence is. So if I just have a list of items, that's a sequence. And let's get into some examples of sequences here. So a sequence is often given in this format. A sub n equals some formula for the sequence. So say we have a sub n equals 2n plus 5. We would like to find the first 5 terms of the sequence. So if we wanted to find the first term, a sub 1, we're going to put in 2 times my n is 1 for the number of term I'm on plus 5, which would end up equaling 2 plus 5, which would equal 7. Alright, let's do a sub 2. Let's find the second term. That's going to be equal to 2 times 2 plus that 5. So that would end up equaling 4 plus 5, meaning my second term would be 9. A sub 3 would be 2 times the number of the term I'm on, so 2 times 3 plus 5, well that's going to equal 6 plus 5, which would equal 11. Let's find the fourth term. A sub 4 equals 2 times 4 plus 5, well that's going to equal 8 plus 5, which would end up being 13. And then for the final term, the fifth term, a sub 5, that would be 2 times 5 plus 5, so that would end up giving me 10 plus 5, which would equal 15. And in theory, I can do this infinitely. This is how you're going to find any term of a sequence when a specific formula is given to you. In this case, it's a sub n equals 2n plus 5. And the first 5 terms of the sequence are 7, 9, 11, 13, and 15. These would be the first 5 terms of this sequence. And as you see, I have it as a list. It's simply just a list of terms. That's all it is. Let's do some more of these here. Let's say this time I have a sub n equals 2 to the n. So the formula given for my sequence is a sub n equals 2 to the n. Well, let's find the first term. A sub 1, that's just going to equal 2 to the first power, which is simply 2. If I want to find my second term, I'll take a sub 2, I'll set that equal to 2 sub 2, or 2 to the second power, because that ends the term I'm on. Well, 2 to the second power is 4. A sub 3 is going to equal 2 to the third, because that's a third term, so that would be 8. A sub 4 would equal 2 to the n power, or in this case 2 to the fourth power, that would be 16. And then a sub 5 would be, of course, 2 to the fifth power, which would be 32. So again, this sequence can go on infinitely in theory and never stop. But the first 5 terms of the sequence are going to be 2, 4, 8, 16, and 32. And if we wanted to go on to find the sixth term, it would be 2 to the sixth power, which would be 64. Alright, now, what if I change it up a bit here? What if I changed it and I made my a sub n negative 2 to the n power? So now I'm going to have a negative 2 to the n power. So a sub 1 means I take that negative 2, raise that to the first power. Well, negative 2 to the first, that's just going to be negative 2. A sub 2, I'll take that negative 2, raise it to the second power. I would end up getting positive 4. A sub 3 would give me negative 2 raised to the third power. That would actually give me negative 8. Then a sub 4, I'll take that negative 2, raise it to the fourth power. That would give me positive 16. Then a sub 5, that would be negative 2 to the fifth power. That would give me negative 32. So as you see, this time my sequence alternates negative to positive to negative to positive to negative. In fact, we're going to deal with more with alternating sequences in series in Calculus 2. Whenever you have a negative sign raised to a power, that indicates an alternating sequence or series. In this case, it's just a sequence being a list of terms. So the first 5 terms are negative 2, positive 4, negative 8, positive 16, and then negative 32. Those are the first 5 terms, and it'll keep doing this infinitely. Alright, now let's do something a bit different here. Let's say I have a sub n equals n plus 1 divided by n plus 2. So a sub n equals n plus 1 divided by n plus 2. Well, I want to find the first term, so that n indicates the term number I'm on. So a sub 1 is going to end up equaling 1 plus 1 all over 1 plus 2, which would end up giving me 2/3. So my first term is 2/3. Let's find a sub 2. That's going to equal my second term, so 2 plus 1 over 2 plus 2, which would end up giving me 3/4. A sub 3, that would equal the term number I'm on, n, so 3 plus 1 all over 3 plus 2. Well, that's going to end up equaling 4/5. Let's put the fourth term over here. So a sub 4, that's going to then equal, of course, the number of term I'm on, 4 plus 1 over 4 plus 2, which would simplify into 5/6. And then I want to find the fifth term, a sub 5. That would equal my n plus 1, in this case 5 plus 1, over my n plus 2, so 5 plus 2, which would simplify into 6/7. And of course it'll keep doing this infinitely. But the first 5 terms of this sequence are going to be 2/3, 3/4, 4/5, 5/6, and 6/7. Those would be the first 5 terms of this particular sequence. 2/3, 3/4, 4/5, 5/6, and 6/7. Alright. Now we don't just have to limit ourselves to the first 5 terms of a sequence, we can find any term of a sequence. Let's say I have something as like n squared over 2n plus 1. So let's say the formula for the sequence is a sub n equals n squared over 2n plus 1. Well, I want to find the 16th term. So a sub 16, that means I'm going to put in 16 for my term number wherever I see the n. That'd be equal to 16 squared all over 2 times that 16 plus that 1. Well, that's going to end up equaling 256 over 32 plus 1, which will simplify into 256 over 33 And I'm not quite sure if those reduce any further. I don't think so, but let's be sure. Nope. So that's the best we can do. So the 16th term of this sequence would be 256 over 33. And let's do one more where we find a specific term. Let's say I have 2 to the n, 2 to the power of n plus 1 all over 2 to the n power, that quantity plus 1. So the formula for my sequence in this case is, in the numerator, 2 raised to the n plus 1 power divided by my denominator of 2 to the n power, that quantity plus 1. We're going to find the fifth term. So the fifth term, no, actually, yeah, let's find the fifth term. So I'm going to put in 5 wherever I see n, so that would be 2 to the 5 plus 1 power all over 2 to the 5th power plus 1. Well, 2 to the 5 plus 1, that's the same as 2 to the 6th all over 2 to the 5th plus 1. Well, 2 to the 6th, that's 64 over 32 plus 1, which would simplify into 64 over 33. So in particular, the sixth term of this sequence, the fifth term of this sequence is going to be 64 divided by 33. All right, so that's how you find terms of a sequence. Now, let's say you have something like, let's get into factorials here. Let's actually talk about factorials. So it's been since Algebra 2 since we've dealt with factorials. That's simply an exclamation mark called a factorial. What that does is it takes n times the quantity of n minus 1 times the quantity of n minus 2 times the quantity of n minus 3 times dot 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 to infinity. So all this means is you're going to multiply the current number you have times one number less times one number less times one number less infinitely. But let's say you have something like 1 factorial. 1 factorial is simply 1, okay? 2 factorial, that's going to be the same as 2 times 1, which is simply 2. Now if we do 3 factorial, that's going to be 3 times 2 times 1, which we know would give us 6. So 3 factorial is 6. 4 factorial, that's going to equal 4 times 3 times 2 times 1, which would be 24. And then if we had 5 factorial, that's going to be 5 times 4 times 3 times 2 times 1, which would equal 120. Some people think that numbers with an exclamation mark means you're just yelling the number out. No, that exclamation mark is a factorial. It's an operator that takes the number and multiplies it by 1 less continuously until you reach 1. Once you reach 1, you can stop multiplying it. But that is how a factorial operator works. So where am I going with this, you might ask? So let's say you have a sequence in which you have something like 1 over n factorial. You're given 1 over n factorial, and you're being asked to find the 7th term of a sequence. So you'll put in 7 for your n, that would be 1 over 7 factorial, Well, what is 7 factorial? That's going to be 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1. Alright, so let's multiply these. You get 2, 6, 24, 120 times 6 is 720 times 7. Let's take 720 times 7. That's going to be a big number. Or most calculators should have a factorial operator where you can just take the number and push exclamation mark. It'll give you that value. This turns out to be 1 over 5040. So the 7th term of this sequence would be 1540, because 7 factorial equals 5040. So yes, you can get numbers like that too with dealing with factorials. Now, let's see here. Let's say you have something like -1 to the 2n plus 1 all over 2n plus 1, that quantity factorial. So I have the term for a sequence here, -1 to the 2n plus 1 power, that quantity all over 2n plus 1 factorial. And I would like to find the third term. Let's just go for the third term, alright? So a sub 3, that means wherever I see n, I'll put in that 3. So that's going to equal -1 to the 2 times 3, which is 6, plus 1, all over my 2n. 2 times 3 is 6, plus 1 factorial. Well, that's going to equal -1 to the 7th, all over 7 factorial. -1 to the 7th is -1. And then 7 factorial we've already determined was 5040. So that means the third term of this particular sequence is going to be -1 over 5040. Now, of course, we can also simplify factorials. Let's do that. So let's say I had an expression like 2 factorial over 4 factorial. I can actually simplify these. 2 factorial we can leave alone, but 4 factorial you can break down into 4 times 3 times 2 factorial, because it just keeps becoming a factorial of one smaller number until you reach 1. Well, notice in the numerator, your 2 factorial cancels out with the 2 factorial in the denominator. You're left with 1 over 4 times 3, which would just give you 1/12. So the answer we should get here would end up being 1/12. We'll simplify some more. Let's say we have something like 12 factorial divided by 4 factorial times 8 factorial. So now they're spicing it up a bit. We're going to simplify 12 factorial over 4 factorial times 8 factorial. Well, that's going to be, of course, what I would do. Take your 12 factorial, that's the same thing as 12 times 10, 12 times 11 times 10 times 9 times 8 factorial, because that 8 factorial will keep going down till you reach 1. 8 factorial is a much simpler way to write this, divided by your 8 factorial times your 4 factorial. Alright? Well, notice your 8 factorials will cancel out. What you have now is you'll have 12 times 11 times 10 times 9, and it stops there because the 8 factorials are gone, but you still have this 4 factorial to deal with. Well, what is 4 factorial? That's the same thing as 4 times 3 times 2, and there's an implied 1 there. We don't really need to write the 1. Well, notice between the numerator and denominator, we have a 12 that'll cancel, right? 4 times 3 is 12. That'll cancel with the 12. Now we just have a 2 here in the denominator. That'll definitely reduce with the 10. The 2 will be gone. 10 divided by 2 is 5. So what you have now is simply 11 times 5 times 9, which would equal 495. So once we simplify this, we get that 12 factorial divided by 4 factorial times 8 factorial equals 495. Let's do one more of these, then we'll do some algebraic factorials. How about, so we have 10 factorial times 3 factorial divided by 4 factorial times 6 factorial. We have a bit of a mess here, don't we? Well, let's take a look at this here. So the largest factorial in the numerator is 10, the largest in the denominator is 6. That tells me that we should probably expand that 10 factorial down to 6 factorial in the way that you would get 10 times 9 times 8 times 7 times 6 factorial. You could stop there. Then you still have your times 3 factorial. All that divided by your 6 factorial times your 4 factorial. Well, notice now between numerator and denominator, your 6 factorials will cancel. So that just made the numbers a little bit smaller. So now in the numerator, you'll have 10 times 9 times 8 times 7, and then you just have times 3 factorial divided by your denominator of 4 factorial. Well, we can definitely expand that 4 factorial into 4 times 3 factorial. Okay, well, look at this here. 4 times 3 factorial. You have a 3 factorial in each the numerator and denominator that'll cancel out. What else do you have? 4 goes into 8 perfectly 2 times, so the 4 will be gone. That 8 will turn into a 2. So what you'll be left with is 10 times 9 times 2 times 7. Alright, 10 times 9 is 90, times 2 is 180 times 7. Let's take 180 times 7 and see what we get. We get 1,260. So this expression simplifies into 1,260 once we cancel out factorials. So that's how you do that with numbers. And there is a point to why I'm doing factorials, because we're going to have some sequences and later on even series that involve them. So let's say we have something like, algebraically, we have n plus 1 factorial divided by n factorial. How the heck are we going to simplify that? It's really not as bad as it looks, because factorial means you take the number and multiply it by 1 less constantly until you reach, well, in this case it would be infinitely, but we're not going to go on infinitely, because if we look here, n plus 1 factorial would just turn into n plus 1 times n factorial. And you could stop there because you have an n factorial in the denominator, which means these n factorials will cancel out, and this will just reduce to n plus 1. So that actually reduced pretty nicely just down to n plus 1 because we were able to cancel out n factorials. Now, what if we had n plus 2 factorial over n factorial? So we have n plus 2 factorial over n factorial. Okay, so that n plus 2, that can turn into n plus 2 times n plus 1. Now, when we're expanding algebraic factorials, we want to look to see if we're ever going to have a hope of canceling anything out in the numerator and denominator. We definitely do, because after n plus 1 just comes n factorial, which now you also have an n factorial in the denominator, and they will cancel out between denominator and numerator. This would just leave you with the quantity of n plus 2 times n plus 1. And it would be sufficient to write it like that. If your professor is really gung-ho on it, you could FOIL this out and get a quadratic, but I don't think that's necessary. This would just simplify into n plus 2 times n plus 1. Alright, now we have it switched around. We have 2n minus 1 factorial all over 2n plus 1 factorial. Notice this time the bigger number's in the denominator. Believe it or not, we're still going to do it relatively the same way. You're going to take your bigger number, see if you can expand it out till you can have a hope of canceling anything out between the numerator and denominator. So this would turn into your numerator. We can just leave that alone, 2n minus 1 factorial all over that 2n plus 1 factorial turns into 2n plus 1. Now if you take 1 away from that, you'll just have that times 2n. Take 1 away from that, then you'll end up having 2n minus 1, and we're going to stop there, so we'll put the factorial sign. Notice now between numerator and denominator, we can cancel out a 2n minus 1 factorial, which should just reduce to 1 over 2n times the quantity of 2n plus 1. That's exactly what we would get when we reduce the factorials. 1 over 2n times 2n plus 1. Alright, so those are algebraic examples. Now, we are also, what we had before, what we worked with in the beginning, were called explicit formulas. So we had explicit formulas that you could use to find any term of a sequence. Now we're going to do something called recursive formulas. And let's say they give you that the first term is going to be 6, and they want you to find the first 5 terms of a sequence where a sub k plus 1 equals a sub k plus 2. Unlike an explicit formula where you can find any term, a recursive formula requires you to know previous terms. So we already got the first term. To find the second term, so that k is, to find the second term, you're going to take your first term plus 2. So a sub 1 plus 1 is going to equal a sub 1 plus 2. That's how that would work. What does that mean? That means that a sub 2 equals my a sub 1, which is 6 plus 2, which means my second term is 8. Now if I want to find my third term, a sub 3, since it would just be 2 plus 1, that's going to equal my a sub 2 plus 2, Well, a sub 2 was determined to be 8. Then add that 2, you would get 10. Let's find the fourth term. So a sub 4, that's going to end up equaling my a sub 3 term plus 2. Well, a sub 3 was 10, so we'll take 10 plus 2, that'll equal 12. And then if we want to find the fifth term, a sub 5, that's going to equal my a sub 4 plus 2, which would end up giving me 12 plus 2, which is 14. So using the recursive formula, I got the first 5 terms of the sequence. We have 6, 8, 10, 12, and 14. Those would be the first 5 terms of the sequence using this recursive formula. You could think of it like regression. That's how you could think of recursive. You have to know a previous term in order to find the next term. Whereas in the explicit formula, you're able to find any term out of order. Let's do another recursive. So a sub 1 equals 14. A sub k plus 1 equals negative 2 times a sub k. That's another example of a recursive formula. So if I want to find my a sub 1 plus 1 term, in other words, a sub 2, I need to take negative 2 times my a sub 1 term, my previous term, which would be negative 2 times my a sub 1, which is 14, which would give me a value of negative 28. So a sub 2 is negative 28. All right, let's go on to find a sub 3. So a sub 3, that's going to equal negative 2 times my a sub 2 term. Well, negative 2 times what is a sub 2? That was negative 28. That would give me a value of positive 56 for my third term. Let's do a sub 4. That's going to equal negative 2 times my a sub 3 term. So that would be negative 2 times positive 56, which would equal negative 112. And let's find my a sub 5 term. That's going to equal negative 2 times my a sub 4 term. So that would equal negative 2 times negative 112, which would give me positive 224. So using this recursive formula, to find the next term, you just take the previous term and multiply it by negative 2. So my first 5 terms are 14, negative 28, positive 56, negative 112, and then positive 224. Those are the first 5 terms of the sequence. All right, so that's using recursive formulas. Now we're going to be given some lists, and we need to come up with the general term, an explicit formula for the sequence. So let's say you just have something like 1, 4, 7, 10, 13, and it just keeps on going and going, right? We don't know where it's going to stop. This is an infinite sequence. That means it can literally keep going till kingdom come and we still won't be done. So we need to find a general term for the sequence. Well, what's the first term? A sub 1 is 1, right? Now we notice that between each term there's a difference of 3, right? There is a common difference of 3. A sub 2 would equal my a sub 1 plus 3. a sub 3 would equal a sub 2 plus 3, which this is building on a recursive formula, but we can get to a general term. Now, you have a common difference of 3, so we're going to build the a sub n. If I literally take 3 times my term number n, and I subtract 2, so if I put in 1 for my first term, I take that, I get 3 minus 2, I get 1. If I put in 2 for my second term, 3 times 2 is 6, minus 2 is 4. 3 times 3 is 9, minus 2 is 7. 3 times 4 is 12, minus 2 is 10, and it just keeps going. Now, we're not going to worry about this term today, but a couple lessons from now, there's something called an arithmetic sequence, which this actually is, because it has a common difference. But you notice you have a difference of 3. So if you multiply every term by 3 and subtract 2, you'll end up with the general formula you need to find the next subsequent terms. Now, 3, 7, 11, 15, 19, ... So we have another sequence that, again, it'll go till kingdom come, but you have 3, 7, 11, 15, and 19. Okay, so what's your first term? Your first term, a sub 1, is 3 in this case, right? We have a common difference of 4. We'll call that D. We have a common difference of 4. So if I want to find the general formula, what if I took 4 times a number and I subtract 1? So 4n minus 1, right? So if I put in 1 for my first term, 4 minus 1 is 3. Put in 2 to get the second term. 4 times 2 is 8, minus 1 is 7. 4 times 3 is 12, minus 1 is 11, and you see this pattern holds. So the general formula in this case would be a sub n equals 4n minus 1. Again, this is actually an example of another arithmetic sequence, but we'll teach on arithmetic sequences in particular in a couple lessons. Now here's a bit of a different one. You have 0, 3, 8, 15, 24, and it just keeps on going and going and going. Alright, and the name of the game to find a general formula for sequences is to be able to spot patterns, of course. But look between the first two terms. Yes, your first term is 0. You have a difference of 3 between the first and second term, but if you look between 3 and 8, you have a difference of 5. If you look between 8 and 15, you have a difference of 7. If you look between 15 and 29, you have a difference of 9. 15 and 24, you have a difference of 9. So there is no common difference between each of these. How the heck are you going to express something like that? Let's picture some other sequence related to this in a second. So what if I do a similar sequence of 1, 4, 9, 16, 25, ... Look at this, okay? This sequence is literally off by one number from this sequence. 1, 4, 9, 16, 25. Well, isn't it true that this sequence would mean that to find the term you need, you're literally just going to take your number of the term you're on and raise it to the second power, right? So if I take 1 to the second power, my first term, I get 1. I take 2 to the second power, I get that 4. I take 3 to that second power, I get 9. I take 4 to that second power, I get 16. I take 5 to that second power, I get 25. So the pattern for this sequence seems to be holding that you take whatever term number it is and square it. Well, what does this tell you about this sequence then? You're literally off by one single digit for this sequence. So that means for your original sequence, if you take this one, that n squared, and just subtract 1, you'll have the general formula for your sequence. A sub n would equal n squared minus 1. And that holds true. 1 squared is 1, minus 1 is 0. 2 squared is 4, minus 1 is 3. 3 squared minus 1 is 9, minus 1 is 8. 4 squared is 16, minus 1 is 15, and it just keeps going and going. So sometimes it's not readily apparent from this particular sequence you've been handed, but if you can set up a very similar sequence and then see if you have any differences between them that you can easily relate to, you can get something like this. In this case, it's the normal a sub n equals n squared, just off by one number. It's just one less number. Alright, so now we have 1, 1/4, 1/9, 1/16, 1/25, and it just keeps going and going and going. So you have an infinite sequence again. You have 1, 1/4, 1/9, 1/16, 1/25. We want to find the general term of a sequence. Well, I think it's safe to say a sub n is going to equal 1 over some denominator, right? Your numerator is constantly 1, and if that pattern continues, your numerator will always be 1. We don't even got to worry about that. But what about your denominator? If you look at your denominator, it looks like you just take the number of term you're on and square it, right? It looks like a sub n should be 1 over n squared. So if 1's your first term, so 1 over 1 squared would just give you that 1. 1 over 2 squared gives you 1/4. 1 over 3 squared gives you 1/9. 1 over 4 squared gives you 1/16. 1 over 5 squared gives you 1/25. So in fact, the general formula for this particular sequence would be a sub n equals 1 over n squared. The whole idea of this is to be able to spot patterns. Alright, now we have 1/2, negative 1/4, (1/8), negative 1/16, and it just keeps going and going and going. This is just going to keep on going and going and going, but you notice you have an alternating positive, negative, positive, negative. So we have to address that alternating. So we have a sub n, of course. That's how you'll begin to list every general term of a sequence if you're finding an explicit formula, which we are. That's going to equal, since we have an alternating positive and negative, you're actually going to take -1 to some quantity. Now, if I just took -1 to the n, I would end up getting -1 for my first term in the numerator, where actually it should be +1. So what if I took -1 to the n minus 1? Well, 1 minus 1 is 0, right? -1 to the 0 is +1. Now, what about our denominator? Well, it looks like it just goes up in powers of 2, right? 2 to the first would be 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, and so on. So my denominator should just be 2 to the n. So this pattern should hold then to give me these terms. So my general formula in this case, if I put in 1 for n, I would get negative 1 to the 0, which is positive 1 over 2, so I get 1/2. To find my second term, if I take negative 1 to the 2 minus 1, that would be negative 1 to the first, which is negative 1 over 2 squared, which is 4. I get that negative 1/4, and it keeps on going and going. So in this case, the explicit formula for this sequence is a sub n equals negative 1 to the n minus 1 over 2 to the n. Alright. This one shouldn't be so bad. What if we had 2/3, 3/4, 4/5, 5/6, 6/7, and it just keeps on going and going. So we have this sequence. We have 2/3, 3/4, 4/5, 5/6, 6/7. Well, definitely start with a sub n. That's how you'll define the explicit formula for a sequence. Your first term is 2, right? If I just take n plus 1 for my numerator, so 1 plus 1 is 2, my second term should be 2 plus 1, which is 3. My third term should be 3 plus 1, which is 4, so the pattern seems to hold for the numerator. But how about the denominator? Well, if I take 1 plus 2, I get 3. So, and then if I take 2 plus 2, I get 4. 3 plus 2, I get 5. So this pattern seems to hold. So the general explicit formula for a sub n for any term of the sequence is going to be n plus 1 over n plus 2. All right. Now, what if I have this one? 1 plus 1, 1 plus 1/2, 1 plus 1/3, 1 plus 1/4, and it just keeps on going and going and going. So this just keeps going and going and going, like the Energizer Bunny. That's been a while, but I think it's safe to say every term has a 1. That's pretty easy. So a sub n for the general formula, the explicit formula, that definitely equals 1, plus, we have a plus straight across the board. All of your numerators are 1, right? And then your denominator seems to be based off of what term number you're on. The first term, second term you get 2, third 3, fourth 4, and so on. So the general formula, the explicit formula for this particular sequence is a sub n equals 1 plus 1 over n. That one shouldn't have been so bad to spot. Now, let's change it a little bit here. We have, let's see, 1 plus 1/2, 1 plus 3/4, 1 plus 5/6, no, actually I took a wrong turn there. Hold on a second. It's actually going to be 1 plus 7/8, 1 plus 15/16, 1 plus 31/32, and it just keeps on going and going and going till infinity. It'll keep on going and going. So in this sequence you have 1 plus 1/2, 1 plus 3/4, 1 plus 7/8, 1 plus 15/16, and then 1 plus 31/32. So always let's start with a sub n for the explicit formula. every term has a 1, so that much should be obvious, and it's plus whatever number comes next. Actually, let's not focus on the numerator of the fraction. Let's focus on the denominator first. Because notice my denominator seems to go up in multiples of 2. If I take 2 to the first, I get 1, 2 to the second, 2, 2 to the third, 8, 2 to the fourth, 16, 2 to the fifth, 32. So my denominator should definitely be 2 to the n, right? 2 to whatever power. Now take a good look at your numerators. Aren't these values exactly one number less than your denominator? So your numerator should end up being 2 to the n, that quantity minus 1, right? Because it's exactly 1 less than your denominator. So the explicit formula for this sequence should be a sub n equals 1 plus 2 to the n minus 1 over 2 to the n. That one looked horrific, but it's really not as bad as it looks. Only got a couple more here, then we'll be done with the lesson. Oh, good one. Good one. We have 1, 1/2, 1/6, 1/24th, 1/120th, and it just keeps going and going and going. Well, this one may not be so apparent because they definitely don't have a common difference. In fact, they don't even have a common multiple at all. They don't have a common ratio or a common difference, so there's no hope of doing it basically. But what do we know here? Your numerator is 1. I want you for a moment to forget your numerator. Just forget your numerator, okay? Look only at the denominator. Isn't this here the same, the 1 the same as 1 over 1, right? Well, we have 1 over 2. Then we have 1 over 6. Then we have 1 over 24. Then we have 1 over 120. And then it just keeps going, right? There's an even better way to look at this here. Let's really break down the denominators. So I still have 1 over 1, right? Isn't it true that 1 over 2 is the exact same thing as 1 over 2 times 1? Now what about 1 over 6? Isn't 1 over 6 the same thing as 1 over 3 times 2 times 1? And then what about 1 over 24? Isn't that true that it's the same thing as 1 over 4 times 3 times 2 times 1? And you're probably starting to see where I'm going with this, but let's expand out to 1/20th, the 1/120th. The 120 is the exact same thing as 5 times 4 times 3 times 2 times 1. Now, what operation do we know that expands numbers out by one less number? You keep multiplying by one less number until you get to 1. That's the factorial function, right? That's going to be the factorial function that does that. So this is why I took the time to teach you factorials, because these come up all the time in sequences and series. The next lesson, series, we'll talk about what a series is, but for now we're on sequence, but it's used in both. So now let's go for the general term of the explicit formula of the sequence. A sub n equals your numerator of 1, that's a given. And it appears that whatever term you're on, it's that number factorial. So a sub n should equal 1 over n factorial. That would be the general explicit formula for your sequence. A sub n equals 1 over n factorial. I got one more I want to do. Then we'll be done with the lesson. Now this one throws a curveball at you. So we have 1, 2 squared over 2. 2 cubed over 6. 2 to the 4th over 24. 2 to the 5th over 120, and then so on. So you're probably looking at this and thinking that in the denominator it's going to be an n factorial again. And in truth, you're right. You're absolutely right. Okay? It's going to be in that form. But notice something here. Look at your numerator even. So let's set up our a sub n, right? Actually, no, let's not even do that. Why don't we do this here? So, what is 1? That's the same thing as having a denominator of 1, right? 1 over 1. 2 is the same as 1 over 1. Now, 2 squared, of course, that's 2 squared. Then you'll have it over 2. Well, then you have 2 to the 3rd over 6. Well, isn't 6 the same thing as 3 times 2? And then what about the next term? You have 2 to the 4th. Well, isn't 24 the same as 4 times 3 times 2? And really times 1. We just don't really need to put that times 1. And then we have 2 to the 5th over 120, which is the exact same thing as 5 times 4 times 3 times 2. And then, of course, your sequence is just going to keep going. Well, first look closely at your numerator. Let's set up the a sub n. What if I were to tell you that all of these are powers of 2, even the 1? Alright, so on your second term, you get a numerator of 2. Your first term, you have a numerator of 1. So, and then your third term, you have a numerator of 2 to the 2nd. Your fourth term, you have a numerator of 2 to the 3rd. Fifth term, you have a numerator of 2 to the 4th. Notice that that power of 2 is one number less than what your term is. What does that mean? That means your numerator should be 2 to the n minus 1, right? If I want to find my first term, 2 to the 1 minus 1 is 2 to the 0, which is 1. Find my second term, 2 to the 2 minus 1 is 2, which is, yeah, it's just 2. 2 to the 3 minus 1 is 2 squared. 2 to the 4 minus 1 is 2 cubed, and so on. So this pattern holds for the numerator. Now what about the denominator? And notice something, it looks like your factorials are also one behind the current term. Right? Another piece of trivia that's going to help you, and I forgot to mention it earlier, what happens if we have a 0 factorial? That just equals 1. It's universally accepted in the field of mathematics that 0 factorial equals 1. So if that helps you, just understand that. What if I took this over n minus 1 factorial, right? So if I'm doing this on the first term, 1 minus 1 is 0. 0 factorial we know is 1. The second term is going to be 2 minus 1, which would be 1 factorial, which also happens to be 1. The third term, 3 minus 1, is 2 factorial, which happens to be 2. Fourth term, 4 minus 1 is 3 factorial, which is 3 times 2, which gives you that 6. Let's do one more. If I take the fifth term, 5 minus 1 is 4. Well, 4 factorial, so that's 4 times 3 times 2, which gives me that 24. So yes, the general explicit formula for this sequence is going to be a sub n equals 2 to the n minus 1 all over the quantity of n minus 1 factorial. Alright, so that's it for sequences. These do tie into series. So the next lesson we're going to get into a series and what that is and how these relate to series. So I hope everyone has a great day. Take care.